So welcome to the 21st lecture of surface engineering. In the previous lecture, we discussed two very important types of transformation products in steel, namely the pearlitic and benedict transformations, both of them arising out of eutectoid transformation. Only the phase aggregate, the product aggregate, is different in these two cases, and also they followed two different transformation mechanisms. But today we are going to talk about martensitic transformation, which is very different in terms of mechanism, product morphology, and the path taken. And the basic difference arises from the fact that martensite is a non-diffusion control transformation product, or so-called shear transformation product, as against diffusion control transformations of the other varieties of pearlitic and benedict transformation. So let me just clarify this part right away, that when we talk of diffusion controlled, then what we mean is that in a given lattice, if we have atoms which are located in certain positions like this, when the atoms move, they move from one designated position to the next, and so exactly the distance of separation from one jump, or the length at which an atom will jump from one to another position, will be exactly the multiple of interatomic distances. When we talk of shear, then the two neighboring atoms, when there is a migration, the migration will not be exactly up to the next position of the atom. It will be rather in the somewhat in between. So the distance of separation will not be integral, but fraction of interatomic distances. So when we talk of diffusion, then we are talking about migration by interatomic distances, exactly interatomic distances in a given crystallographic directions on a given plane. Similar thing when we are talking about shear, then we are talking about migration of atoms from one position to the next, which is not exactly distance equal to the interatomic distances, but a fraction of that. And this happens because of certain other reasons and under certain other compulsions, which we will discuss later. But another important part that I would like to tell you is that, for example, when we talked about the TTT and the CCT diagrams, and in the TTT or CCT diagrams, we said that if this is the so-called TTT diagram, the corresponding CCT would be somewhat like this. And we said in order to get martensite, which is this is the martensite start line, let's say. So in order to hit this line without intersecting the pearlite start or bainite start and finish, we need to employ a very fast cooling rate. And this gap, since it is less than a second for plain carbon steel, we actually need to employ a very drastic quenching. So whenever you actually quench a hot steel component into some bath containing some fluid so that you can extract heat faster, we would like to avoid this zone. So whenever we drop a hot body into a certain fluid, there will be immediate formation of vapor blanket around, and that will retard the heat transfer. And this is what is going to happen in the first stage. So during the quenching process, we would like to minimize this first stage as low as possible, and would like to employ the second stage as much as possible, so that the heat transfer is the fastest and uniform during this stage. Now, when we talk of martensite, we need to understand that here the product is not going to form in equiaxed shape, like growth in all directions to the same extent. This will not happen in case of martensite. Since it is a process dictated by shear, and shear of set of atoms in a given direction only by fraction of interatomic distances. So if that shear happens in this particular plane, another shear happens in another plane, so these are all parallel crystallographic planes, and when the shear happens in them, the degree of shear is going to be different, and as a result of which the morphology or the shape of the product that we develop will be more like a lenticular shape. That is because typically we may say that if this is the mid plane, and if the shear is happening to different extent as we go from bottom to the top, and also happening similar things below the dividing plane, then the overall shape of the product will look like a lens or a lenticular shape, and a half of it will appear as a needle shape. So, needle or a spear shape. So, this needle or spear shape is typical of martensite as opposed to the polygonal shape of any other diffusion control transformation product. So, this is the kind of a shape is what we always expect. And typical microstructure, these are all sketches, but this is a real time microstructure in steel, plain carbon steel. This is in alloy steel, and this is in iron nickel system, where we actually happen to see a morphology which clearly tells us there is a very large influence of orientation influence of orientation for the growth of these kind of martensitic plates. So, we if we move on, we also need to understand that where is this martensite coming from. So, for example, the initial reactant is austenite, which is interstitial solid solution of carbon in gamma iron, the FCC iron, and this, in case of pearlite, we would have, or bainite, we would have expected ferrite and cementite to form as a two-phase aggregate. In case of martensite, what we expect is a product which is either body centered tetragonal or low tetragonality cubic system. So, the crystal structure changes without any change in composition. So, if you initially are dealing with FCC austenite, so this is the contour of such an FCC unit cell, and in this FCC unit cell, what you have will be the 6 atoms at the 6 face centering positions and 8 atoms at the 8 corners. So, you have 4 effective number of atoms per unit cell. But now, if this crystal structure or this unit cell, because of very large compulsion and no time given, suddenly changes or is forced to change into and take up a new crystal unit cell, the possibility exists whereby you now have to consider these 4 atoms on the top plane, these 4 atoms at the bottom plane, and one more at the center, which earlier was the face centering position. So, now we are looking at formation of a new unit cell out of the existing FCC unit cells. So, 2 neighboring FCC unit cells, from the 2 neighboring ones we have squeezed out a new unit cell, whereby the length here is exactly the same as the length in this direction. So, the length is exactly A naught, but on the other 2 directions the lengths are now shortened, squeezed by an amount of A naught over root 2, because this length is you can easily calculate that this length will be root 2 A, and half of that will be just A upon root 2. So, this means that earlier an FCC unit cell where A, B and C were all equal, and we had 4 effective number of atoms per unit cell, is now transformed into a new unit cell which has 1, 2, 3, 4 and 5, 6, 7, 8. So, 8 atoms at 8 corners, but so effective number is only 1 and 1 in the center of the unit cell. So, another, so 2 per unit cell, but the difference is that this axial length is different than the two other axes. So, from this part, the product what actually emerges is going to be a tetragonal unit cell, because A is equal to A. So, in x and y direction they are equal, but in z direction they are different. So, A is equal to A, but not equal to C, and this is possible if we assume that as if the entire transformation is happening due to some readjustment of such a change in crystal structure from FCC into body centered tetragonal. But this is hypothetical. In reality, this kind of a Bain distortion model is not valid, but good enough for us to understand as to how tetragonal crystal lattice can emerge from existing face centered cubic lattice without necessitating any large scale rearrangement of atoms, except that the atoms need to just move by fraction of interatomic distances from one position to the next and allow such new unit cell to emerge. So, this is the overall microstructure. This is a real time microstructure. And one other thing what we should know is that the amount of carbon is very important in developing such tetragonality. For example, here it is manifested in terms of a surface dependent property called hardness as a function of carbon. So, if we increase the amount of carbon, the hardness of the steel increases, and that is purely because the supersaturation in martensite increases with more and more addition of carbon. In fact, the distortion that we were talking about now is better understood here. So, typically in a BCC lattice, which is what you expect at room temperature. So, FCC tries to transform to BCC, but the carbon which has the option of going either into this face centering position of the BCC unit cell or middle of the edges. So, this would have octahedral coordination and this would have a tetrahedral coordination. So, if it chooses either of these positions, for example, if it goes to the middle of the edges, then we see there is immediate lattice expansion in this direction. So, it is exactly because of this reason in a tetragonal unit cell where you expect that the C direction to be larger than the A and B direction. So, this tetragonality or deviation from the cubic geometry is going to be larger if the amount of carbon is more. So, in fact, that is exactly what we see, that as we increase the amount of carbon, the hardness of steel which is coming from martensite increases, and this is felt until about a certain limit of addition of carbon. So, this is an empirical relationship which actually says that if you increase the amount of carbon, the tetragonality, the C over A ratio increases, and because of which the hardness increases. But when you actually pump in more or dissolve more amount of carbon, it is not only the tetragonal martensite, but even in austenite, which is the parent phase where from martensite actually forms. Even in austenite, the lattice parameter increases, and so does in case of the C axis of the tetragonal martensite, but you see a certain amount of contraction. So, that is what we saw already in our previous slide, that in the Bain distortion model, that the C axis expands, whereas the A and these two axes they contract. So, carbon plays a very important role in defining the tetragonality of martensite in terms of these two lattice constants, and eventually that determines the overall mechanical property of martensite. We also have understood that this is a process whereby no large scale solute partitioning takes place, and transformation is through shear, which essentially requires the atoms to move only by fraction of interatomic distances and not by integral multiple of interatomic distances. So, now actually I decided to make a summary for you to follow the martensitic transformation in the nutshell. So, first of all, the name martensite comes from the German scientist, metallurgist, who actually first proposed the existence of martensite in steel because of fast quenching. So, it is the hardest solid solution phase possible in steel. We are talking about not the hardest phase, but hardest solid solution phase. because the hardest phase in iron carbon system is the interstitial compound called cementite. So martensite is usually hard, and in fact it is because of this strength we always are so much interested in martensite, but there is no necessity that martensite always have to be hard. For example, if you go to iron nickel system or titanium nickel system, the martensite that forms are called thermoelastic martensites, and they are actually in asquench condition, they are not necessarily very hard. The strength of those martensites arise because of, or those alloys arise because of another phenomenon which follows the transformation, and that's precipitation hardening. Now, martensite again is not necessarily occurring only in steel, it can occur in very many non-ferrous systems. In fact, I have listed a large number of systems here. These are ferrous systems, but you see martensite can also arise in many other alloys which are not necessarily steel, which are non-ferrous alloys. It can happen even in non-metallic systems, for example, in zirconia, which is an oxide. It can happen in various minerals, solidified gases at ultra low temperature, in various inorganic compounds, and even in polymers. So, though we often tend to believe that martensite is almost the prerogative of steel, but that's not true. So, what is important for us to know is that martensite is a product of a transformation of a particular mechanism of transformation, and is a generic name, not only confined to steel. It can happen in other systems as well. But in this surface engineering course, the reason why we are discussing so much about martensite or pearlite or bainite is because a large number of components, large number of bodies, large number of engineering applications are based on steel, and when we want to improve upon their life or their performance, we do carry out certain transformations onto the surface which employ exactly the same type of phase transformations that we are discussing so far. But the most important thing in case of martensitic transformation is the nature, which is diffusionless. That means the atoms move not by integral multiple of distances, but by fraction of interatomic distances. It happens at very low temperature, where diffusion is very low. In fact, that's one of the reasons why, for example, when you quench all the way from 800 to room temperature, the diffusion coefficient actually decreases by orders of magnitude, and at room temperature or below room temperature, the diffusion coefficient is so low that it will take years for any transformation which is possible at high temperature to happen at room temperature. So, there is no thermally activated migration involved, and atomic transport is purely by shear, and which again I must reemphasize is by a fraction of interatomic distances. Another very important feature is that there is no change in composition. So, when you talk of pearlite or bainite, you start with austenite and there is immediate solute separation, so that two different phases form like ferrite and cementite. Ferrite would typically contain a carbon to the tune of 0.025 weight% carbon, whereas cementite will have 6.67 weight% carbon. So, from about, let us say, if you are dealing with a 0.4 or 0.6% carbon steel, which is what will austenite contain. So, from 0.6% carbon, you swing all the way to two different phases of alpha and Fe3C, which if this contains, let us say, 0.6% carbon. So, you are now talking about a phase compositional variation as large as this. In case of martensite, there is no such no such solute segregation or solute separation. So, whatever carbon you have in gamma will be retained in martensite. In other words, you actually produce a highly supersaturated solid solution. We will come to that as to why martensite is so hard. This kind of a transformation where crystal structure changes, but composition does not change, is very similar to the allotropic or polymorphic changes or even massive transformations. But here all these again the point of distinction is that allotropy or polymorphism or massive, these are diffusion control transformations, whereas martensite is a shear transformation product. Martensite is also a heterogeneous process. So, nucleation occurs typically at grain boundaries or different martensite plates or even dislocation tangles and so on. But the nucleation barrier is very, very low and also the interfacial energy is very low. So, nucleation, so typically in any nucleation process, when we talk of this barrier in case of martensite is very, very small because the interface actually is of very low energy. So, martensite can actually form in the can actually manifest in the form of plates, laths or needles. I am sorry, there is a spelling mistake here. It can be, but it is always confined within the parent grain, which is the parent grain of austenite. So, if this is the parent austenite grain and if martensite plate forms, it can go all the way up to the boundary, but never crosses and moves to the other crystallite across the boundary. Now, the morphology usually, as I said, is of lenticular shape. So, typically you would expect a lens-like shape, and if you see the half of it or take your section is such that you are viewing at a different angle, so you tend to see such needle-like or spear-like structure. But you also can have instead of lenticular or lath type, you can also see butterfly or plate type or midrib structures and so on in primarily in non-ferrous systems. Martensite is the hardest solid solution because of very many reasons. Most important is the supersaturation. Higher the amount of carbon, greater the supersaturation and greater is the strength. Also because it has very small plate size, I would rather not use the term grain because we are not talking about polygonal shape, we are talking about large aspect ratio, lenticular or plate or spear-like shape. So, very small plate size. The crystal structure is BCT, which is certainly less plastic and has less number of slip systems available compared to the parent austenite, which has an FCC. There is a lot of internal strain involved because of the contraction and expansion in two different directions. Martensite contains a large density of dislocations because of the large stresses created during the transformation, and you have very few or very poor slip systems. So, all these are important reasons as to why martensite is the hardest solid solution. The transformation is irreversible because unlike in case of say pearlite, where you actually go to ferrite and cementite combination, but when you reheat you get back the austenite. In case of martensite, austenite transforms to martensite, but when you reheat martensite, you do not necessarily get back austenite. You actually martensite dissociates into pearlite, which is ferrite plus cementite, and then if you reheat, then you go back into austenite. So, this is not directly reversible transformations, but in some other systems they can be completely reversible. For example, titanium nickel, iron nickel, and it is because of these reasons these classes of alloys typically show the phenomenon called shape memory, which is totally absent in case of steel. Now, the transformation occurs basically below a temperature called martensite start. Now, typically if you again refer to the CCT diagram, now let us refer to the CCT diagram. So, you will see there an MS martensite start and MF, which is martensite finish transformation, which are just lines and not curves. They are lines because martensite is an athermal transformation. It is not temperature dependent, it is a temperature dependent, but it is not thermally activated process. So, you require so much of driving force in terms of undercooling, but once you start, even if you hold here for infinite time, the volume fraction of the phase will not change. The volume fraction of phase of martensitic product will change only when you go to lower and lower temperature. That means, when you increase the driving force in terms of undercooling. In case of diffusion control transformations, we all know that if we hold at an isothermal condition, the product volume fraction increases with time. So, that is a time dependent transformation. Martensite, being an athermal process, is a time independent transformation. We must know that martensite actually is a very rare transformation which occurs at very high speed, almost at the speed of propagation of sound, but with a coherent glacial interface. We did talk about the role of crystal defects, and generally we did discuss at that point of time that if an interface is coherent, then the mobility is generally very low. But here we are seeing a very rare combination where we are saying that the interface is coherent and yet highly glacial, so much so that it can move at a pace which is almost equal to the velocity of sound. The temperature, the so called MS and MF temperatures can be raised to slightly higher level by applying Plier deformation, and then the start temperature is called martensite deformation, martensite transformation start by Plier deformation. So, MD is a raised level of MS by way of because of Plier deformation, because these Plier deformations produce lot of dislocations which act as nucleation sites for martensites. So, hence even with slightly lower undercooling, normally you require so much undercooling, but even with slightly lower undercooling, now martensite can start nucleating because of the presence of large density of dislocations due to Plier deformation. Now, we generally the volume fraction and the plate size of martensite you can control by the extent of cooling or heating, and in fact, in some other systems actually they can behave completely reversibly, so called thermoelastic or rubber like nature, but this is not in steel, but in some other non-ferrous systems. I already mentioned, and let me repeat, that the growth occurs by cooperative shear displacement. So, essentially if one plate moves this much, another plate moves this much, another this much, another this much. So, until the mid plane the degree of shear varies. In other words, from the mid plane as you go up or away from the central plane, the degree of shear actually decreases, and as a result we end up seeing such lenticular shape. So, this lenticular shape develops because of that. Now, when the transformation takes place, actually there are one can define a certain reference plane called the invariant or the habit plane, where martensite usually nucleates. Now, if you compare with plastic deformation, we always say that dislocations are prone to move or finds it easy to move in slip systems comprising closely packed and loosely stacked. So, essentially we are talking about planes which are wide apart, but very closely packed. So, the atoms should almost touch each other. In case of martensite, we see just the reverse. Remember, for diffusional transformations, we require closely packed and loosely stacked planes. In case of martensite, we actually require atoms which are rather wide, that slightly wide apart, but very close by. The planes are very close by. So, just the opposite. For martensitic transformation, we require wide apart but closely packed planes, and these kind of planes, this kind of restriction actually brings us to the possibility of seeing this transformation occurring on some specific types of planes called habit planes, which is described here. For example, in iron 30 nickel alloy, or typically in steel, or in some other alloys, there will be certain planes where such kind of transformation or martensitic transformation is favored, and that is purely arising out of the fact that for shear you actually require atoms slightly apart, so that the atoms can move by fraction of interatomic distances and not hop from one place to the very next possible position. This invariant deformation that happens in case of martensitic transformation leads to invariant plane strain, and there is, of course, there is no slipping, but there could be, this can lead to formation of certain amount of twin. So, it is quite commonplace that certain martensites actually would be largely twin martensite. in case of non-ferrous systems, this invariant plane strain can create stacking faults. So that's also sort of crystallographic defects, which further makes deformation or deformability difficult, and in the process increases the strength. The most important point part that we must remember, that entire driving force for martensitic transformation primarily comes from primarily is of chemical nature, which essentially means that if this is the austenite we are talking about, and if this is the eutectoid point, when we quench all the way to very low temperature, so this is in terms of the phase diagram, and in terms of the kinetic diagram, if this is the austenite start, and if we are quenching all the way from way above austenite start and quenching way below, then this large delta T is proportional to a very large supersaturation, and this is exactly the driving force for martensitic transformation. So when you make life so difficult that you are quenching all the way from above 800 to room temperature or below, in this very large decrease in temperature quenching, you are not allowing any time at all for diffusion to take place. So there is no pearlite, no bainite, and then the solution austenite has to transform because it is highly metastable because of this very large undercooling, and the only way it can now transform is by shear, by fraction of interatomic distance movement, and not by diffusion control transformation, where atoms move by integral multiple of interatomic distances. So it's time to recapitulate. So in this last half an hour or so, we have discussed only about martensite, and of course at times compared with pearlite and bainite. I think by now it's clear to you that the martensite is a shear transformation product, where atoms move by fraction of interatomic distances, retains the entire supersaturation, the entire amount of carbon that you had in austenite. You need drastic quenching so that you don't allow any diffusional transformation like pearlitic or bainitic to intervene and weaken or reduce the supersaturation. We discuss as to what are the other possible reasons, like lack of slip systems or relatively complex crystal structure like body-centered tetragonal, a very small size of the plates or the platelets, and so on. Because of all these reasons, we see martensite as the hardest solid solution. The growth mechanism is completely different compared to pearlitic or bainitic, and for that matter any other diffusion control transformation, including allotropy or massive transformations and so on. Why is martensite relevant to surface engineering at all? Is purely because very soon we will start discussing about various techniques for surface hardening, and whenever we talk of surface hardening of steel, we will definitely invoke the concept of formation of martensite onto the surface. And we would rather like to create a situation where we transform the austenite, we heat the surface to austenitic state, make it austenite, and then subsequently by rapid quenching onto the surface, we convert the surface into martensite, but not the core. So the core can very well be retained as pearlite, so that the toughness is retained and the ability to absorb energy is retained, but the surface becomes predominantly martensite, so that it can withstand or resist wear or any other kinds of degradation. We talked of briefly, we alluded to various possibilities of martensite being non-hard or not as hard as in steel, and that's typically in case of non-ferrous systems. And we also found out that martensitic transformation, or this shear type of transformation as a generic mode of transformation, is possible in very many systems, even in non-metals, solidified gas, ceramics, oxides, even in some polymers. But finally, one question that we should ask ourselves, that if martensite is so good and so beneficial, would we care to have 100% martensite in the bulk or on the surface? The answer is no. The answer is no, and you have to find out as to why 100% martensite is not desirable. And I can give you only one hint, that though martensite is very hard, martensite also is brittle. So it cannot absorb energy, and hence it can lead to easy formation of cracks. So thank you very much.